Today, I want to talk about probability density functions. Well, first, I'm going to look at a histogram. This is not a histogram which represents frequencies. This one is a histogram which represents probabilities. So we have on the vertical axis, instead of frequency density, we've got probability density. The important thing about any histogram is that the area represents, in this case, the probability. So if I want to know the probability that my x value is between these two marks, I'm looking for the area of that red rectangle. Just like any normal frequency histogram, it would be probability density times the width. The height of the rectangle is the probability density, the width. Multiply them together, we get the area. Well, what I'm really interested in today is the general shape of the histogram. The blue curve shows the general shape of the histogram, and if I was to use the blue curve as an approximation to the red rectangles, then the probability that my x value was between these two black marks would be the area, not of the red rectangle now, but the area under the curve. So instead of thinking of the red rectangles, I can think instead of the curve, which will give me approximately the same answer. The area of the red rectangle is the probability between those two marks, or we could talk about the area under the curve as being approximately that. Well, we must be somewhere within all the red rectangles. If we must be somewhere there, the probability, therefore, that we are within these red rectangles must be 1. The area of all those red rectangles must be 1. If the blue curve is going to represent some sort of probability type curve, in fact, a probability density curve, then the area under that curve would also have to be 1. Here is another example, this time with a larger number of rectangles. The same principles apply. We have probability density, and the area of this red rectangle is the probability that x lies between where the arrow is now and where the arrow is now. We can see the general shape of my probability histogram with the blue curve, and the same idea applies, that the probability of being between two values of x is approximately the area under the curve. The area of all the red rectangles must be 1. The area under the curve must be 1. Another example, this time with even more red rectangles. Each rectangle now is getting thinner. The blue curve is a better approximation than it was in the earlier ones. The area is still what matters. Some of you might by now be thinking of the normal distribution, where you worked out the area under the curve as the probability between two values of x. You also know that the area under the normal probability curve is 1. Same sort of idea is happening. This is just a much more general case of it. Well, what happens if we increase the number of intervals still further? As we increase the number of intervals more and more, and the rectangles become narrower and narrower, we don't really need the blue curve to show us the general shape. And we are still in the situation where the area under the whole setup is 1, the area under the blue curve if I was to draw it is 1. A probability can never be negative, so we could never get any of these rectangles below the axis. My blue curve, if it was there, would never be below the x-axis. What I have been describing is what we call a probability density function. They don't all have to look like this. You'll see some very different shapes, but basically a probability density function, it might be 0 at certain points, and above the axis, down again, it might be 0 beyond. There are two vital things about this. One, it cannot go below the x-axis. You cannot have a negative probability. And if it's going to be a probability density function, the total area must be 1. So if something satisfies those conditions, we have what is called a probability density function. Here is just some general curve, any old curve. And between the values of L and R, this curve happens to be positive. Outside, it is 0. Well, it satisfied one of the conditions that I mentioned for a probability density function. It is never negative. The other condition is that the area under the curve between L and R must be 1. We can use these curves in the same way as you used the normal distribution curve when we met it in S1, that if I want the probability of being between A and B, I simply want the area of this part of the diagram, the area under the curve between A and B. I've summarized that here. A continuous random variable. We now have a continuous variable. There are no discrete pieces. It's like the normal distribution. The normal distribution is continuous. A continuous random variable has probability density function f of x. This is the new name that we are meeting. The conditions are that the total area under the curve has to be 1. In this instance, the only bit that we need to consider is between L and R, so the integral from L to R of f of x dx has to be 1. The curve never goes below the axis. We can't have negative probabilities, which tells me that f of x has to be greater than, or it could be equal to, 0 for all values of x. And then there's this last bit, the probability that we are between A and B is just the area under the curve, which is the integral A to B of fx dx. So those are the essential parts of a probability density function. There are two more things I want to say about a probability density function. One is that when you're drawing or sketching the curve of a probability density function, you should always include the 0 bits. The function is 0 here. That is part of what you should be describing in your sketch. 0 there. The other thing is this. It really doesn't matter if we're talking about the probability of being less than B or being less than or equal to B. The probability that we are less than B is the area up to B. The probability that we are less than or equal to B is the area up to B. All that we've done is to add this straight line. And a straight line has no area. Just following on from that statement, the probability that x equals B must be 0, because the area of that line, the area from B to B, is 0. That doesn't mean that B cannot be happening. In any continuous situation, the probability of any particular value is always 0, but it does not mean that it cannot happen. I've summarized that here. Outside the interval, you must draw the red lines to show the 0. X less than b, x less than or equal to b makes no difference. And this is the bit you must remember. X equals b is 0. That must be true for a continuous function. And this does not mean that x can never be equal to b. Well, let's now look at an example showing how we can put all this together. Suppose that x is a random variable with probability density function f of x is k times x times 4 minus x squared for 0 less than x less than 2 equals, and outside that region f of x is 0. Find the value of k. Well, what do we actually know about a probability density function? We know that it can never go below the x-axis. You should be able to see that with x between 0 and 2, this bracket must always be positive, that must be positive. So if f of x has to be positive, we do know that k has to be positive. What else do we know about a probability density function? Well, we know, or we should be able to remember, it's not much to remember, that I want a darker blue, sorry. Let's change to dark blue. The area under the curve, so that's the area from x equals 0 to x equals 2, must be 1. That is the point that I stressed several times about probability density functions. That tells us that the integral from 0 to 2 of k x 4 minus x squared dx must be 1. Well, let's do that. I like to take the k out. Integrating the 4x gives me 2x squared, and integrating the x cubed gives me x to the 4 over 4 between 0 and 2. Put the 2 in, and we get 2 times 2 squared is 8, minus 2 to the 4 is 16 over 4 is 4. So that is 4k. This is the area under the curve. That, therefore, is 1. And we've worked out quite easily that k must be a quarter. Whether this probability density function is any practical use or not, I don't know. Doesn't really matter. At the moment, we're simply looking at conditions for a function to be a probability density function. This cannot be negative as long as k is positive, and when k is a quarter, the area is 1. Okay, let's move on a little bit. Find the probability that a half is less than x is less than or equal to 1. Well, f of x, because it's disappeared over the top, let's just remind you what it is. It's k, which we worked out was a quarter, of x times 4 minus x squared. And that was in the region between 0 and 2. So half to 1, we're still okay. The probability between a half and 1 is the area under the curve The equals makes no difference, remember? So we're looking for the area under the curve of a quarter x, 4 minus x squared dx. Well, we integrated it just now, and that was, if I keep the quarter outside, 2x squared minus x to the 4 over 4, between a half and 1. And that, if we work that out, which I'm sure we can all do, is 81 over 256, which is perfectly acceptable as an answer, or we could write it as 0.316, and I would give that to 3 significant figures because I was using my calculator. Very simple, just a nice application of a principle that you're used to with the normal distribution. Probability that you are between two values is the area under the curve. In this case, we can integrate or anti-differentiate to find the answer. With the normal distribution, it is not possible to anti-differentiate, so you have to use your probability tables. What happens now if we try to sketch the graph of y equals f of x? We know that f of x is a quarter of x, and I've written that one the wrong way around, 4 minus x squared. And we know, therefore, that we have a cubic equation. Let's just rewrite f of x, factorizing. We get a quarter x, 2 minus x, 2 plus x. So just a little bit of thinking over here. If I have some axes and I want to sketch that curve, it must go through the x-axis at 0, at 2, and at minus 2. And it is a cubic with a negative x cubed. Negative x cubed must look something like that. Not as wobbly as that, but then that's me drawing it. So we know that between 0 and 2, we are expecting the curve to do something like this. Perhaps I could make that just a little bit better. That's it, I got there this time. So that is part of my answer. Let's get rid of the rubbish over here because I don't really like it. And the other part of my answer is that it is equal to 0 otherwise. And that is the bit that I warned you about and told you you would have to make sure you draw it, that you must draw the 0 pieces. Let me get that up onto the axis for you, I hope. That's better. And we need the 0 piece on the other side. Still not started in the right place, but never mind. There we are. So when drawing that curve, we draw the piece that comes from knowing that it's x cubed. The maximum is just a little bit on the right of 1, but nobody's going to be that particular with a sketch. And then we have the 0 pieces on the outside. So that's just a little example showing you most of what goes on. You can find more about this in your textbook. S2 on pages 37 to 43.